Hi everyone. We're going to start chapter 14 in chemistry today, and chapter 4 deals with the topic of thermodynamics, and we started some of this in the last chapter, and we'll continue discussing principles of thermodynamics in chemistry in this chapter. Before we do that, last chapter there were a couple things that we did not quite get to, just two brief definitions that will help us in discussing the concepts within this chapter. And those two definitions are kinetic energy and potential energy. So kinetic energy is energy that is due to motion. And potential energy is energy that is stored. So a simple example of these two would be, let's say that you have a ball and you are at the top of a hill with that ball, but the ball is just sitting on the ground and it is stationary. Well, that ball has potential energy by virtue of its position at the top of a hill. But then if you let the ball begin to go down the hill, then the potential energy the energy that was stored in the ball due to its position then gets converted to the energy of motion, or gets converted to the energy of kinetic energy. So those two terms are important because they also apply to chemical reactions, and we'll get to that in just a moment. So potential energy is energy that is stored. Kinetic energy is the energy that is associated with motion. So one of the big concepts in chapter 14 is called enthalpy. We can't really talk about enthalpy in a chemical reaction as enthalpy. So what we talk about instead is we talk about the change in enthalpy. So we talk about the change that happens within a chemical reaction. So enthalpy is energy. So the change in enthalpy is the change in energy that occurs within a physical change or a chemical change. So the change in energy that occurs. And of course, for us, we're going to mainly be talking about enthalpy with regard to chemical changes, and how does energy change within a chemical reaction. The symbol that is used for the change in enthalpy is delta H. Okay, so delta H stands for the change in enthalpy. Two concepts that we did discuss in the last chapter were exothermic and endothermic reactions. So in an exothermic reaction, now if we can now use the terms potential energy and kinetic energy in an exothermic reaction, what is happening is you are converting potential energy to kinetic energy. Okay, so converting potential energy to kinetic energy. So what that means, if you're converting potential energy to kinetic energy, then potential energy, which we'll abbreviate PE, is going to decrease. So the potential energy is going to be less than what you started with. And so in an exothermic reaction, delta H will be negative because the amount of potential energy that you the amount of potential energy that you start with will decrease as it gets converted to kinetic energy. So in an exothermic reaction, delta H, the change in energy, is going to be a negative number. Okay, then conversely, we can look at endothermic reactions. And in an endothermic reaction, you are converting kinetic energy into potential energy. So KE, kinetic energy, to PE, which is potential energy. So in this case, what the potential energy will increase. And so in an endothermic reaction, potential energy increases. Therefore, delta H, or enthalpy, the change in enthalpy is positive. Okay, so one way that the way that you can tell whether a reaction is exothermic or endothermic is to look at delta H. If it's positive, it's an endothermic reaction. If delta H is, so this is endothermic, and if delta H is negative, then it is an exothermic reaction. So let's look at some comprehension checks. Let's look at comprehension check number 1, and this is on page 419 in your book. Okay, so this is comprehension check 1, page 419. Okay, so in that one we are given 3 different delta H's. The first one is delta H is equal to negative 1.73 kilojoules per mole. The second one in a different reaction is that delta H is equal to 5.14 kilojoules per mole. And then the third one is that delta H is equal to negative 16.8 kilojoules per mole. Okay, so we first want to know whether each reaction is endothermic or exothermic. So remember, if delta H is negative, it's an exothermic reaction. So this is exothermic. And this one also would be exothermic. And if delta H is positive, then we know that it is an endothermic reaction. And then the second part of that says if we assume equal moles of the reactants, which one will feel the hottest? So in an endothermic reaction, that kind of reaction is going to get colder. Last week when we mixed vinegar with baking soda, that was an endothermic reaction, and the temperature decreased. So this will get cold. The exothermic reactions will get hot, and so then we look at the energy associated with them, and it's because the energy associated with this is more than the energy associated with that, then this one will be the hottest. This one will still get hot, but not as hot as this last one. Okay, so in terms of the order, the middle one would be cold. Both of these would be hot, so this would be hotter, but then this one would be the hottest. Okay, so the important things to remember here are that exothermic reactions have a negative delta H and endothermic reactions have a positive delta H. Okay, so let's, I'm going to draw a chemical reaction here by using Lewis structures. I'm going to move this down a little bit so I have room to write it. Okay, so this reaction is that we have two hydrogen gases plus an O2, and that is going to give us H2O. There's two waters, okay? So this is it's a combustion reaction. So right, you're gonna when you add oxygen to something, that's a combustion reaction. So it's the combustion of hydrogen gas. The bonds that hold these elements together contain energy, and so that allows us to look at enthalpy within a chemical reaction. So in other words, enthalpy relates to bond energy. Now, the other thing to think about is that this bond energy is potential energy, so it's energy that's stored within these chemical bonds. So if we can look at what happens to the bond energy, then we can get some idea of the change in energy associated with a chemical reaction. So in order for this reaction to proceed, what has to happen? Well, in order for this reaction to happen, we have to pull apart these hydrogen bonds here. And we also have to pull apart these oxygen bonds. So we have to pull apart the oxygen atoms, and then the hydrogens and the oxygens have to rearrange themselves and become bound to and bind to each other. So in order to break these bonds between the hydrogens and between these oxygens, that requires energy. So breaking these bonds requires energy. So we use energy to break the bonds, and then when we form these bonds, that's going to release the energy that was used to break the bonds. Okay, so forming the bonds releases energy. Breaking the bonds is going to use energy. It's going to absorb energy. So if we can think then in terms of our of delta H, or the enthalpy related to a chemical reaction, delta H is going to equal the energy for breaking bonds minus the energy for making bonds. Okay, so this is energy for breaking the bonds minus the energy for making the bonds or forming the bonds. So if you have a negative delta H, that means that more energy was used than was released. So more energy used. So more energy was used to break the bonds than is released from forming the bonds. So more energy used than released. So that would be an exothermic reaction. Okay, and then conversely, if delta H, if you have a positive delta H, that means that the energy to break the bonds was greater than the energy to make the new bonds. So this would be an endothermic reaction. So we've said that previously, that a positive delta H is an endothermic reaction and negative delta H is an exothermic reaction. Fortunately, there are tables available to us to tell us the bond energy that is associated with different molecules. So bond energy is the amount of energy that's required to break one mole of a bond. So energy to break 1 mole. So the larger the bond energy, the stronger the bond that exists between the atoms making up that molecule. The larger the bond energy, the stronger the bond between the atoms. So one of the things that we're going to look at that table in just a moment, but so one of the things I want you to notice is, we're going to look at single bond. We're going to have some molecules that are just single bonds, but then we'll have some double bonds and some triple bonds. And you'll notice that, and we've said this when we learned about single, double, and triple bonds, but when we look at the bond energy, you'll notice that it takes more energy to break apart a triple bond than it does a double bond, and it takes more to break a double bond than it does a single bond. And I'm going to put a chart up here to show you that. So the larger the bond energy, the stronger the bond is between those atoms, and therefore it's going to take more energy to break those bonds. Okay, so let's look at a table. Okay, so this is a table of bond energies associated with bonds between different atoms. So here we see that a hydrogen to hydrogen bond, it requires 436 kilojoules to break that bond. And then here's a carbon and oxygen bond. So carbon-oxygen bond requires less energy than the hydrogen to hydrogen bond. It requires 350 kilojoules of energy to break that bond. And then I mentioned double and triple bonds. So here's a carbon double bond. So a carbon double bond takes 611 kilojoules per mole. Here's a nitrogen-oxygen double bond. It takes 670 kilojoules of energy to break 1 mole of that substance. Here's an oxygen double bond, 498. And then we have some triple bonds. So here's a carbon-oxygen triple bond. It takes 1,072 kilojoules of energy to break a mole of a carbon-oxygen triple bond. And here's a nitrogen-nitrogen triple bond. It takes 945 kilojoules of energy. So you can see that the larger this number, the stronger the bond between them, and so it takes more energy to break them. So here on this chart we see that of the ones that are listed, the carbon-oxygen triple bond has the highest bond energy, and therefore it would be hardest to break apart. Let's see, the lowest I see, I guess, is this oxygen-chlorine single bond. No, actually here's a fluorine. Okay, so that two fluorine atoms bound together require 159 kilojoules of energy to break that bond. Okay, so this would be this is a much weaker bond than this bond. So let's go back to the problem that we were looking at previously, and I need to get that. I want to get that chart up again. So I'm gonna make this smaller and put it up here in the corner so we can refer to it. Okay, so there's our chart for bond energy. So then let's take this chemical reaction that we saw before. Okay, and we drew that as this. So we had two hydrogen bonds. I'm just going to put these below each other just to save space. And then we had an oxygen triple bond, or double bond, sorry. So the little structure for that would look like this. And then the product is going to be two water molecules. It's going to be there's one water molecule, and then we need to fill in the rest of the electrons here, and then another water molecule. Okay, so if we want to look at the enthalpy of this chemical reaction, delta H is equal to the energy of breaking the bonds minus the energy of forming the new ones. So, in other words, we're going to take the energy required to break these bonds between the hydrogens and to break this double oxygen bond, and we're going to subtract from that the energy that is required to form these hydrogen-oxygen bonds that exist in water. Okay, so let's look at what has to be broken. So what has to be broken in this chemical reaction is we have to break two of the HH bonds. Okay, so there's one there and there's one there, and we have to break one oxygen double bond. Okay, and then what has to be formed? So it's going to be the energy of broken minus the energy of form. Well, what has to be formed is we have to form hydrogen-oxygen bonds, and to get two water molecules, there's four of those. So there's one hydrogen-oxygen bond, there's two, there's three, and there's four. So formed, we're going to have four hydrogen-oxygen bonds. Okay, so then let's look at the energy, let's look at the numbers associated with that. So the two hydrogen-hydrogen bonds. So this chart tells us that each hydrogen-hydrogen bond requires 436 kilojoules, and we have two of those. So we're going to take 2 times 436 plus, now we have one oxygen double bond, so that's this. That's going to take 498 kilojoules. Okay, so that's the energy associated with breaking the bonds on this side of the equation. And then what we're going to subtract from that is the energy of forming. So that means we have 4 hydrogen-oxygen bonds, and that's here. So each of those is 460. So it's going to be minus 4 times 460. Okay, so if we do the math related to that, what we will end up with is that delta H is equal to negative 470 kilojoules. Okay, so that tells us that more energy was required to break the bonds on the reactant side than to form the new bonds on the product side. So this is an exothermic reaction. So energy will be released from this kind of reaction. Okay, so that's how we do, that's how we look at the change in enthalpy for a chemical reaction. One thing I should mention here is that when charts list bond energy, so if we look at this nitrogen-oxygen double bond, it doesn't matter whether that is written like this. It doesn't matter whether it's written like this or like this. It's the same thing. Okay, so the bond energy associated with that is the same. It's the same type of chemical bond. Okay, so let's look at comprehension check number 2. And at this point, it will be helpful for you as we're working these problems. You'll need to refer to the bond energy table that is on page 420. So you'll want to get your book open to that page. Okay, so comprehension check number 2, which is on page 422. Okay, so we'll look at that problem, and you can just flip over one page to 420 to look at the bond energy chart. Okay, so here's the reaction. Carbon monoxide plus water will give us CO2 and hydrogen gas. Okay, so we want to know what is the bond energy, or what is the enthalpy associated with this chemical reaction. Okay, so I'm going to draw Lewis structures for the carbon monoxide. So it's going to be a triple bond oxygen. And then I guess this will have, and there's just one of those. And then you're going to have a water molecule. So H, so draw the Lewis structure for that. Put in the dots here. And then you'll have a CO2. So the Lewis structure for CO2 looks like this. We need to put our electrons there. And then you'll have a hydrogen gas molecule. So hydrogen to hydrogen bond. Okay, so remember we have to break these bonds. We're going to break these bonds, and we're going to compare the energy associated with breaking those bonds to the energy with forming these bonds. Okay, so we have on the breaking side, we have one carbon to oxygen triple bond, and we have two oxygen to hydrogen bonds. Okay, there's one, there's two, so two OH bonds. The energy, if you look at your chart, the energy associated with this is 1072, and the energy associated with the OH bonds is 460, but we have two of those, so it would be 460 plus 460. Okay, so the energy associated with forming those bonds will be the sum of those. So the energy of breaking the bonds would be 1072 plus 460 plus 460. So that's 1992. Okay, and then we look at the what's involved in forming these bonds. So we're going to have this on this side. We have two carbon to oxygen double bonds. So we have one here and one here, and then we have one hydrogen to hydrogen bond. So looking at the chart on page 420, the carbon oxygen double bond is 732. So this is going to be 732, but there's two of those. So 732 plus 732. And then the hydrogen double bond is, or the hydrogen bond is 436. Okay, so if we add all that together, 732, so this is 1900. Okay, so we're going to take the energy of breaking the bonds minus the energy of forming those bonds, and so then the answer is delta H is 92 kilojoules. All of this was adding and subtracting, so what we have to do is we have to look at significant figures. The last significant figure here, this is not a significant figure. So the last significant figure is actually in the tens place. So this would actually be 90. So delta H is equal to 90 kilojoules. Okay, so is this an endothermic or an exothermic reaction? Delta H is positive, so it's an endothermic reaction. In other words, it took more energy to break the bonds than it did to form new bonds. Okay, so that's how we do the problems related to enthalpy and bond energies. There are some of those in the review questions at the back of the chapter. I recommend you do those, and we'll go over some of those in class next week. So then I just want to review that So delta H is the energy for breaking bonds. Minus the energy for forming bonds. If this number is positive, it's an endothermic reaction. If the answer is negative, it is an exothermic reaction. Okay. We are now going to discuss something that is called Hess's law. As it relates to enthalpy. And Hess's law states that when determining enthalpy, you have to consider the phase of the compound, because phase does affect potential energy. Okay, so unfortunately, with the bond energies that we just looked at, we didn't really look at the phase of the bonds, but Hess's law states that the phase has to be considered because phase does affect potential energy. So that to do that, we have to think about something that is called a state function. So enthalpy is a state function. And what it means to be a state function is that in a chemical reaction, it doesn't matter what path the chemical reaction takes, the energy involved will be the same. So it doesn't matter the path. The amount of energy absorbed or released is the same. That's what it means for something to be a state function. Your book has kind of an everyday example of, on page 423, there are some paths through a mountain, and you're traveling from point A to point B. The total distance that you travel and the work that you did is not state functions, because if you travel on one of the paths, you're going to travel a longer distance. However, the final altitude that you end up at within that figure is a state function. So in other words, it doesn't matter which path you follow, you're going to end up at the same altitude. And so therefore the altitude is a state function. So the same is true of a chemical reaction. according to Hess's law, and that is it doesn't matter how the chemical reaction happens or the path that it takes, the energy associated with it will be the same. So there are tables associated with chemical bonds that are called standard enthalpies of formation. And before we look at that table, a couple things to keep in mind. One is that these standard enthalpies of formation tables only work, they were developed at 298.15 degrees K, which is 25 degrees C, which is basically room temperature. Okay, so these numbers could not apply for reactions performed at anything except room temperature. So when you look at the chart, you'll see a little 0 next to the numbers, and that, or next to the units, and that 0 symbolizes or signifies that this happened at these values are true at 298.15 degrees K. And then the other thing so the way we signify delta H of formation is we do delta H with a little subscript of the letter F. So this is delta H of formation, and the delta H of formation for any element is 0. And that's true of any element in its natural phase. So remember that the homonuclear diatomics, their natural phase is this, right? Or this, or this. So any element, so carbon would be 0, aluminum would be 0, but then remember that for the homonuclear diatomics, this is their natural phase. So the delta H for any of these homonuclear diatomics would be 0. Okay, so because of Hess's law, what we usually assume is that when we look at a chemical reaction, we assume that it happened by a formation reaction, even though it may not, because it is a state function. It doesn't matter how you get there. We can assume it's a formation reaction and calculate enthalpy as if it's a formation reaction, because it doesn't matter how you get there, the energy associated with the reaction is the same. So let me give you an example here. So if we have this, and remember I said that Hess's law also tells us that the phase is important. So we need to make sure that we pay attention to the phases. So since enthalpy is independent of path, or it doesn't matter how you get to the CO2 and water, we can calculate the reaction as if it actually happens, or we could use some other pathway. So one easy way to do that is we can break down all of the reactants into their elements, and we can then use those elements to form products. And if you add up the double H's of everything that's involved, if you add up the delta H's of everything that's involved, then you're going to get the energy associated with the reaction, even though it may not have actually happened that way. Because it's a state function, you can use it. You can do that to calculate the delta H. So let's look at a table of standard enthalpies of formation. Okay, so let me shrink this up and move it over here. Okay, so your book makes this a little more complicated than it needs to be, but what you need to remember is that to get the delta H of a chemical reaction, we are going to take the delta H of the products minus the delta H of the reactants. Your book on page 425 gives you, it says A, capital A plus lowercase b, uppercase b. They make it more complicated than it needs to be. So you're going to take the delta H of the products minus the delta H's of the reactants. Okay, so for this particular chemical reaction, we would take the delta H of the CH4, then we'd take the delta H of the oxygen O2, and we would remember that that's 0, right? And then we would find the delta H of CO2 in its gas phase, and the delta H of water in its gas phase. So then we would take these, so the delta H of the products minus the delta H's of the reactants, and that would give us the enthalpy of the entire chemical reaction. Okay, so let's do an example. So here is our here's the chemical reaction that we'll look at. Sorry, that's and this is actually a chemical reaction that we've done in class. We use some yeast to speed up the reaction. This is hydrogen peroxide, and you may remember that we said that hydrogen peroxide decomposes into water and oxygen. So to get the delta H for this reaction, we would take the products minus the reactants. So we'll have 2 waters plus 1 oxygen, that's the product side, and then we're going to subtract from that the 2 hydrogen peroxides. Okay, so if we look at the standard enthalpies of formation. So I'm looking at the table on page 424. You need to be looking at that. So the two waters, and the waters are in the liquid phase, so we have to remember that. The oxygens are in the gas phase, and the H2O2 is in its aqueous phase. So the two waters in the liquid phase, it's 2 times negative 285.8 plus, this is going to be 0, right? Because that's oxygen in its natural state. Okay, so that's going to be 0. So that's the product side. And we are going to subtract from that 2 times the hydrogen peroxide in its aqueous phase. So H2O2 in its aqueous phase is negative 191.2. Okay, so on the left side we have 2 times 285.8. So this, and it's negative, so this is negative 571.6 kilojoules minus a negative, because this is negative 2 times 191. So minus a negative 382.4 kilojoules. So negative 571. Subtracting a negative is adding. So the delta H is equal to negative 189.2 kilojoules. So that tells us that this is an exothermic reaction. Okay, let's look at another example. What if we have this reaction? Okay, so there's a reaction. We want to know what is the delta H of this reaction. So we're going to take the delta H of the products minus the delta H of the reactants. Okay, products minus reactants. So we have 2 CH4s plus 3 oxygens on the product side. And we are going to subtract from that the 2 carbon monoxides plus the 4 waters. And we have to make sure that, so this is a gas, this is a gas, this is a gas, and this is a gas. So everything is in the gas phase. Okay, so 2 CH4s, looking at, this is going to be 2 times negative 74.9. So I get that number just from the standard enthalpy of formation chart on page 424. And then 3 oxygens, those are going to be 0, right? Because this is oxygen in its natural state, so plus 0. So this here is all the product side. So 2 times negative, so this is going to be negative 149.8 kilojoules. Okay, and then we're going to subtract from that the two carbon monoxides in a gas form. So each of those is negative, so it's going to be 2 times negative 110.5 plus 4 times the water in the gas is negative 241.8. Okay, so 2 times negative 110 that's going to be negative 221 plus a negative 4 times negative 967, 967.2. Okay, so this is negative 221 minus 967.2. So this whole side over here is going to be negative 1188.2. Okay, so then what we have is we have negative, so we have the product side, negative 149.8 kilojoules minus a negative 1188.2 kilojoules. Subtracting a negative is adding, right? So 149.8 plus, so our answer is 1038.4 kilojoules. So delta H, and that is an endothermic reaction. Okay. So we took the delta H is associated with the product side minus the delta H is associated with the reactant side, and got the calculated delta H, and then because it's positive, it is an endothermic reaction. Okay, so I'm gonna do let's do a couple more of these, and then maybe we'll finish up for today. So let's do comprehension check number 3. So we're given this reaction. Okay, so there's our reaction. So we're going to take the products minus the reactants. So NH4 Cl in its solid state, and we just have one of those. So NH4 Cl as a solid is negative 314.6 kilojoules. And then we're going to subtract from that the HCl as a gas and the NH3 as a gas. Okay, so the HCl as a gas is negative 92.3, and NH3 as a gas is negative 400 or 45.9. Okay, so we're going to have negative 314.6 kilojoules minus negative 92.3 minus 45. So this whole thing is negative 138.2 kilojoules. Okay, so a negative, subtracting a negative is a positive. So 314.6, so negative 314.6 plus 138.2 gives us negative 176.4 kilojoules as the delta H for this chemical reaction. So it's negative, so that is an exothermic reaction. Okay, and then let's do comprehension check number 4. So in comprehension check number 4, the chemical reaction, it says use Hess's law to determine delta H for the complete combustion of C2H6. So that's a gas. And it's at 25 degrees, so that we can use our chart for that. So complete combustion of C2H6 means that we would add oxygen to it, and then we're going to end up with CO2 and water. Okay, so first thing we have to do is balance this chemical equation. And so to do that, I'm going to put a 2 here. Actually, that won't work. If I put a 2, if I put a 4 here, and then put a 2 here, 6 waters and 7 O2s. I think that's balanced now. So we have 14 oxygens. We have 8 plus 6, 14 oxygens, 4 carbons, 4 carbons, 4 hydrogens. Oh no, is that right? No, I'm sorry, this is a H. That's a 6 there. Okay, so 12 hydrogens, 12 hydrogens. Okay, so that's balanced. That's what we have for our, to put together the phases in here. So when combustion happens, you end up with carbon dioxide gas and water vapor. So that's a gas. Okay, so we're going to take the products minus the reactants. So we'll have 6 waters as a gas on this side, and 4 CO2s as a gas on this side. We're going to subtract from that 2 of the C2H6s and 7 oxygens. Okay, so 6 waters as a gas. If we look at our chart, it's negative 241.8. So 6 times negative 241.8 kilojoules. And then 4 CO2s, also in the form of a gas. So it's negative 393.5. Okay, so on this side, So these total up to be 1,000, negative 1,450.8, and then 4 times 393.3. This totals up to be negative 1,573.2. So the total on that side is this is negative 323.2 kilojoules. So that's the product side. And then we're going to subtract from that the reactant side. So we have 2 of the C2H6s in a gas form. C2H6 is 82.6. No, 84.7. Sorry, 84.7. So 2 times negative 84.7. Just get that from the chart. And then the oxygens are going to, the 7 oxygens are going to be 0, right? Because that's the oxygen in its natural state. So we're going to subtract this number. So 2 times 84.7, negative 84.7. It's going to be a minus a negative 169.4. Okay, so do that math. 3,023.2. Subtracting the negative is adding. So add 169.4. So you end up with negative 2,800 and 2,853.8 kilojoules. So it's delta H is negative. So that is an exothermic reaction. Okay, so that is how we do, that's how we relate Hess's law to looking at the enthalpy within a chemical reaction. Okay, the last thing we are going to do today is we're going to look at something that is called activation energy. So what activation energy is that it's the energy that's required to get a chemical reaction started. So chemical reactions need to be given enough energy to get them started. So in other words, you have to give them enough energy to get the reactants moving so that they can collide with each other enough to start the chemical reaction. Some chemical reactions require very low activation energies, And for those, there might be enough energy even just at room temperature to get the chemical reaction going, but others of them require higher activation energies, and that means that you would need to heat up or use a catalyst or something to get those chemical reactions moving. So let's look at a figure that lets us look at activation energies. Okay, so here is a graph of how we could picture activation energy. So the y-axis on this graph is the energy in kilojoules, and then this is just time on the x-axis. So we don't need to worry too much about the x-axis. So here we see that the reactants of this reaction they start out with 500 kilojoules of energy, but then this reaction won't proceed because there's not enough energy. So we put in some energy to get the reaction to proceed, and that amount, so the amount between the amount of energy in the reactants and what you need to get before the reaction actually starts to proceed, is the activation energy. So in this case, it would be 300 kilojoules. We started at 500. We had to put 300 kilojoules of energy into it to get up to 800 kilojoules, and then the reaction proceeds. Okay, so that's the activation energy, and then the reaction will proceed, and you end up with this amount of energy. In this case, 200 kilojoules of energy in the products. Okay, so if the products have 200 kilojoules, so remember, to get the delta H of a chemical reaction, you take the products minus the reactants. The reactants were 500 kilojoules. So the delta H for this particular reaction would be negative 300 kilojoules. So that tells us that this reaction is an exothermic reaction. So we can look at a figure of a chemical reaction and its activation energy and where the reactants start and the products end up with, and we can determine whether it's an endothermic or an exothermic reaction. Let me show you another couple of those. So, I'm not going to ask you to calculate these, but I do want you to be able to look at a figure and tell what kind of reaction it is. Okay, so here we'll just look at the figure. So this would be the amount of energy in the reactants. So 100 kilojoules is the energy of the reactants. And then in order to get this chemical reaction going, we have to kick in some energy. So we went from 100 up to 500. So this amount from here to here would be the activation energy. That's the energy that you have to put in to get the chemical reaction going. And then the reaction will proceed and we end up with 300 kilojoules as the products. Okay, so delta H is products minus reactants. Okay, so the energy in the products was 300 kilojoules, and the energy of the products was 100 kilojoules. So delta H is equal to 200 kilojoules. It's positive, and therefore this is an endothermic reaction. Okay, there are a few more of these. There's actually a comprehension check, so let's look at that together. So we're going to do comprehension check number 6. Okay, so this figure is showing 3 different reactions, and we want to, okay, so we want to answer these questions related to this. So the first one said, which represents the endothermic reaction? So the endothermic reaction would be the one where the energy of the products is greater than the energy of the reactant. So that would be B, okay, because we start at 200 and we end up at 500. So products minus reactants would give us a positive number. So this one is endothermic. And if we look at the others, here's the products, here's the reactants. So here's you're going to have 300 minus 400 products minus reactants. So that's going to be a negative number. So this is exothermic. And the same thing over here. Here's our product. Here's our reactant. So here we're going to have 200 minus 400. That's going to give us a negative number. So that's also going to be exothermic. So numbers 1 and 3 are both endothermic reactions. This one would release more energy because you can just see you're going from 100 to 400. This one is just a difference of 300 to 400. So this one would be negative 100 kilojoules, and this one would be 2 to 4. This one would be 200 kilojoules. Okay, so products, which is 200 minus 400, that'd be 200 kilojoules. So the most energy would be released from this reaction. And then the last question is, which represents the reaction that's easiest to start? Well, the reaction that's easiest to start is the one that requires the least amount of activation energy. So this one, we started at 400. We had to go up to 600 to get it started. So that's just 200 kilojoules to get it started. Here we started at 200. We had to go all the way up to 700. So that one required 500 kilojoules to get started. And this one we started at 400 and went up to 800, so that required 400 kilojoules to get started. So the one with the lowest activation energy would be the one that's easiest to start, so that would be this one. Okay, I think that that is enough for us to do today. What I would recommend that you do before next week, I'm going to give you some problems that you should be sure to get to try to work before next week. So that could, because we'll go over these in class next week. If you can't get them, that's okay. We'll go over them, but at least give it a try. So these are the problems on page 451. And the ones that would be important for you to try to do would be number 3. Let's try number 5. Number 6. Number 7. Number 8. Number 9. I think you could do number 11. And that's it, okay? So if you can make sure that you try to do these problems before, it actually won't be next week, it'll be March 31st when we come back from spring break, so it gives you plenty of time to try to work these. And then we'll start our next session by going over those particular problems. Thanks for your attention. Stay well out there as you are distancing yourself from other people. And have a good spring break.